Welcome everyone to 8.3, okay? Today we're going to be talking about inverse functions, and I like this section. This is essentially branching the past and the future together. After 8.3, we're going to start getting into chapter 9, and chapter 9 is the real heart of this section. So strap yourselves in. And again, at any moment, if at any point you realize, hey, I don't understand this section that we've done, chapter 7 and chapter 8, you need to go back and get comfortable with it, because when chapter 9 comes, we are going to be pulling everything from everywhere that we've learned. So it's very, very important to be keeping up with everything that we've done. All right. So inverse trig function. So let's remind ourselves what inverse functions are. Okay. Inverse functions essentially undo other functions. All right. So the definition, if you want, is f of f inverse of x equals just x. So if you compose and take an inverse function and put that into a normal function, they undo each other, the functions undo each other, and we're just left with that input. Okay? And right, similarly, we could also phrase it like this. They undo each other in this direction as well. So some common inverse functions, right? You may be familiar with this function. C equals 5/9 f minus 32. That's a function. And it has an inverse function. F equals 9/5 c plus 32. These are inverse functions of each other. Well, what are these functions, right? This is a function that takes a temperature in Fahrenheit and translates it to Celsius. This takes a Celsius and translates into Fahrenheit. So if we did the function composition, right? We did f of f inverse, essentially. We'd have 5/9, plug in f, right? If we plug this whole thing in, for that, oops, wrong arrow. For that, we get 9/5 c plus 32, and we still have that minus 32. And if we simplify this, what do we get? If we simplify this, we get 5/9 of 9/5 c. These cancel. Now these cancel to 1. So see how we compose these two functions together? We just get the variable out. Okay, so that's one example of an inverse function. We also talked in previous classes about how do you graphically look at inverse functions. All right, so one inverse function that we talked about was look at if we had a cubic function. This function has an inverse function of the cubed root function. All right. These are inverse functions, and geometrically they have a very, very good, they have a very, very graphical or geometric relationship. Right here, we have the point 8, 2. So over here we have the point 2, 8. Right? And that's going to extend all inverse functions. They're essentially reflections, and specifically they're reflections about this line. These two functions are going to be reflections around the green line. All right, let's look at some other functions. What are some other big functions that we talked about and what their inverses were? These are the big ones. Well, let's use the Fahrenheit and Celsius. Why not? Actually, those are lines. Fahrenheit and Celsius are not really going to be that useful. Here's a silly example. The inverse function of 1 over x is also 1 over x, because notice that this is an inverse of itself, because the blue graph is itself symmetric about the green line. Okay, I'm gonna take 10 more seconds to think of another inverse function that we could talk about. Here's one. E to the x. An exponential function. We said the inverse of an exponential function is a logarithm. Specifically, the red is an exponential function. It has an asymptote at y equals 0, and then it gets really, really big. Blue is the logarithm, has an asymptote at x equals 0, and then slowly grows. You can really see the symmetry on this one, right? The blue is just a reflection of the red. So here we have 0, 1. Here we have 1, 0. All right, and stuff like that. And here we have about 1.5, 4.5. So here we're going to have 4.5, 1.5. All right. Inverse functions are reflections. Now, we talked about a couple other things about inverse functions. If you remember looking about x squared, we said the inverse function of x squared would be, of x cubed was the cubed root of x. So naturally, you might think the inverse function of x squared is the square root of x. But now look at these functions, right? Red and blue should be reflections. These do not look like reflections, right? This does not, the red graph does not have an inverse function. Okay? If we tried to give it an inverse function, it would look like something else. It would look like, oh, I might be able to do it this way. Yeah. If we tried to look at it graphically, this is a reflection. Now the blue is a reflection of the red. But look at this blue. We're talking about inverse functions. And one of the big things about functions, right? We talk about vertical line test. Every input needs to only give us one output. But this certainly fails a vertical line test. This is not a function right here. Okay? So x squared doesn't have an inverse function unless you restrict the domain. So let's do that. I don't know how to restrict domain on Desmos. Let's restrict the domain like this. If we only look at this part of the red, then it has an inverse function. Now we have inverse. Okay? They're reflecting. If we look at the whole domain, it's not inverse, but if we restrict the domain, it's not, because now in this section, the red passes the horizontal line test. All right? And stuff like this. Okay? So let's bring this to sines and cosines. So a function will have an inverse if it passes the horizontal line test. Let's write that down, okay? A function has an inverse if it passes the horizontal line test. So, we're talking about inverse trig functions. Oops, inverse trig functions. A function will have an inverse if it passes the horizontal line test. So, my friends, let's look at the graph of sine of x. Does this function pass the horizontal line test? Horizontal line test says for any horizontal line, we want it to only cross the function once. Let's see. We have a horizontal line here that crosses 1, 2, 3, 4, 5, 6, 7, 8. Yeah, not quite. Not quite. Sine really fails. Really fails the horizontal line test. In fact, sine literally fails the horizontal line test at literally all of its points. Every point on sine of x fails the horizontal line test. So you might say, well, we're talking about inverse trig functions. Sine of x doesn't have an inverse function. We're done. Go home. Goodbye. But that's not how it works. Just like x squared, what are we going to do? We're going to restrict the domain. Okay? So we want to restrict the domain until we pass the horizontal line test. We're still failing the horizontal line test. We're still failing the horizontal line test. But now we pass it. Okay? And that's what we're going to be doing in this section. We're going to be talking about inverse trig functions. And the way that we define these inverse trig functions is going to be by restricting the domain. All right. And notice how far we had to zoom in. And that's the inverse function of sine. Okay, so let's comment about this and make a table. And the way that we're going to guide the guiding properties for how we restrict the domain. Okay, guiding properties. This is important because if you remember this one property, the whole table that follows is going to be much easier to remember. So when, bullet point, when we restrict domains, we either center at 0 or start at 0 and stay positive. So we either positive or 0. Okay? So back to the graph. What's the domain that we're restricting to? Negative pi over 2 to positive pi over 2. Domain is x. What's the range that results? Negative 1 to positive 1. Okay? And remember that the domain of a function is the range of its inverse. Okay? It's very like get motivated material. Stay positive and start at 0. Stay positive or start at 0. So right here we're centering at 0. On a different one, we're going to stay positive. Okay? So what we're going to have here is we're going to have the inverse function. Inverse sine, otherwise known as arc sine of x, looks like this. And it looks kind of funny. But let's change our y-axis real quick. Negative pi over 2. Positive pi over 2 with a step of pi over 4. Now notice our red function and our blue function, they're both functions and they are symmetric. They reflect each other across this green line. All right, this blue function is our inverse sine, otherwise known as arc sine. So let's make a table with function, its domain, and its range. And let's start with inverse sine of x, also known as arc sine of x. They're essentially the same function. We just call them different things. All right? And side note, this is not a negative exponent. This is one of the dumbest things about whoever created this lingo in trig. Okay, let's go off to the side real quick. Right? If I asked you what is x to the negative 1, you would say 1 over x, hopefully. That's what negative exponents mean. But this notation is an inverse function, and it's not 1 divided by f of x. So you might think that inverse sine is 1 over sine, but that's not true. 1 over sine is not inverse sine. We have another function for 1 over sine. It is cosecant of x. Okay, so it's very inconsistent. Mathematicians pride themselves on consistency and logic. Well, we don't pride ourselves on this, okay? So this is not the same as cosecant, which is why a lot of people, myself included, really like the arc sine function. Arc sine is inverse sine. I don't know where the arc comes from, but I believe our book uses some inverse sine like this. But I will be using them both interchangeably. Okay, so remember, the domain of arc sine is the same as the range of sine. And the range of sine is negative 1 to 1. So the domain of arc sine is negative 1 to 1 inclusive. All right, and now what is the range of arc sine? Well, again, the range of arc sine is the domain of sine. What is the domain of the red thing? The x values, negative pi over 2 to positive pi over 2. Again, inclusive. All right. So why is this important? You'll see that later on in the section. This table is the worst part of this section. But if you remember where domain and range comes from, and this bullet point right here, it's going to be a lot easier to remember. Okay, let's add some stars over here. So let's look at other functions. All right. If there's an arc sine, there's going to be an arc cosine. Again, cosine inverse or arc cosine. There's also going to be an inverse tangent, again, or arctan. And we're going to fill in all of these. So let's go back. Cosine of x. Let's see. Cosine of x. Well, I have a bad news for you. Cosine of x is failing the horizontal line test, even when we zoom in to where sine x is. But remember, we had two things that we wanted to talk about. Center at 0 if we can. We can't center at 0 here. If we center at 0, it still fails the horizontal line test. Or start at 0. So what we're going to do, that's the wrong scene. What we're going to do is just slide this over a little bit and start at 0. Because now, what do we have? Now we have a one-to-one function that passes the horizontal line test. And we can look, and this is going to have an inverse function as well. All right. So again, the inverse function here is going to be what we call arc cosine. And don't worry about the blue just yet. Let's forget about the blue for now. Let's find the domain and range of arc cosine. So we're going to look at cosine to find the domain and range of arc cosine. We're going to look at a function to find the domain and range of its inverse, because domain of one is range of the other. So the domain of arc cosine is 0 to positive pi. All right. 0 to positive pi. So that's going to be the range of arc cosine. 0 to positive pi. All right. And the range of cosine is going to be the domain of arc cosine. So the range, we go from -1 to +1. Okay. So that is going to be our domain of the inverse function. Just like sine. So you see some similarities here and some differences here. Okay. So let's actually visually look at these graphs. All right, so it's a little harder to see because I can't restrict the graph in the same way, but here's a graph of arc cosine. It's a weird little guy. If you look at the graph of arc cosine right next to the graph of arc sine, you're going to see something very interesting as well. They're essentially the same shapes. The red and the blue is the same shape, just moved around a little bit. Okay? Which makes sense, right? Because sine and cosine are the same graphs, just moved around a little bit. Secant and cosecant are the same graphs, just moved around a little bit. Sines and cosines, secants, cosecants, arc sine, arc cosine. Anything that has a sine and a cosine with it is going to be related in this mess, in this sense. All right? So let's do the last one, tangent. This is good news right here. Tangent's going to be good news. If we look at tangent, again, it fails the horizontal line test infinitely many places. But if we restrict our domain for tangent, there's a much nicer way to restrict our domain for tangent than for either of the previous functions. Because in tangent, notice it's just this one thing, this whole thing that gets repeated. So let's just look at one of the things. So tangent's really nice here, relatively nice compared to the other things. So we're going to make this, we're going to restrict this from pi over 2, negative pi over 2, to positive pi over 2. See, and now we have a really nice looking function. All right, let's have something like this. All right, so we got a nice good looking function, and now it's 1-to-1. All right. So what is the domain when we restrict it here? Negative pi over 2 to positive pi over 2. That's going to be the range of the inverse function. Negative pi over 2 to positive pi over 2. But this time, oops, this time we're not including pi over 2 because that's an asymptote. So we have a nice parenthesis here. Definitely a parenthesis, not a bracket. Likewise, what is the range of the range of tangent? The range is all the y values. Well, we have every y value we could possibly want here. We have all the y values. So the domain of the inverse function is going to be all of the x values. Now, let's look at it. We have y equals now, let's look at arctangent of x. And we should have, hold on, let's change our grid. Something that is a reflection over here. So see how the blue thing, forget about the other repeated red ones, but notice that the blue thing here is really just a flipped version of one of the reds. Okay, and that's arctangent. Arctangent is actually a pretty cool looking thing. It just kind of zoops like that. And that's arctangent, okay? So one of the big things that we're going to be talking about as we go on in this section is these three things. All right, what is the domain and the range of these things? And it's going to be important. But it's not going to be as bad as you might think. Again, you can always remember why the inverse function either centers at 0 or starts at 0 and stays positive. Okay? So, let's move on. Let's talk some more about inverse functions. If y is equal to the sine of x, we can take the inverse function of both sides. The inverse sine of y then becomes the inverse sine of sine x. Okay. And then the inverse functions cancel each other out for some x's. All right. So not all x's, but this is the general relationship, okay? If y is the sine of x, x is the inverse sine of y. And there's, again, some stipulations here. That's the idea for inverses. So let's really, this lesson, this half of the video is a lot of the theory. The next half, which we'll do tomorrow, is going to be a ton of examples, okay? So this is not probably that concrete yet, but the next half of the video will be where we make it concrete. All right, let's do some examples. All right, so given the below, write a relation involving, oops, that's not how you spell involving, involving an inverse function. All right, so this example is really just to give you some idea, some conceptualization of what's going on. Remember that I made a big deal early on that we are always taking the sine of an angle, the cosine of an angle, the tangent of an angle. And sine, cosine, and tangents are ratios, SOHCAHTOA. So we put in an angle and get out a ratio. Well, with inverse functions, we're going to put in a ratio and get out an angle. Okay, the inputs and the outputs are always switched. If you think of an inverse function as some kind of machine, you put something into the machine, get something out. The inverse function is putting it in the other way and getting back to the start. Okay, it's undoing it. So let's go. So if the sine of some angle, 5 pi over 12, is approximately 0.96593, what is a relationship that we can write using inverse sine? Okay, and you just switch the inputs and the outputs. So with inverse sine, that says that 5 pi over 12 is going to be approximately the inverse sine or arc sine of 0.96593. Okay, the sine of an angle is approximately a ratio. Well, is a ratio. So the inverse sine of that ratio should be that angle. That's the relationship that we're working with. Okay, and we could do this all day, right? The cosine of 1/2 is about, well, it's root 3 over 2, but it's about 0.8776. So 1/2 then would be approximately the inverse cosine of that ratio. All right. You put in, wait. No, I was thinking of something else. Cosine of 1/2 is not anything actually really, really nice. Hold on, let me make sure that I don't have a typo. Cosine of 1/2. Yeah, okay, good. I was thinking of pi over 6. So this is not root 3 over 2. This is something else. Although it's actually close to root 3 over 2. Interestingly enough. Anyway, because pi over 6 is close to 1/2. All right, so we put in an angle. This is 1/2 radians. We put in an angle, 5 pi over 12. We get out a ratio. Inverse functions are the other way around. Okay, so this right here is going to be some angle. This right here, oops, I'm really bad at aiming my arrows today. It's going to be a ratio. Very bad at spelling too. Okay, so let's do one more. This one's a trick question. The tangent of pi equals 0. This is true. But you might think you know where this is going. You might think that this means that pi equals the arctan of 0. But let's consult a calculator. What is the arctan of 0? Arctan of 0 is not pi. The arctan of 0 is actually 0. Okay? This is wrong. The arctan of 0 is actually 0, not pi. Okay, so this relationship, remember, go back here. Inverse functions only hold this way for some x's. And this is where we have to go back to the table, right? We were looking at arctangent of 0. We thought might be pi, but pi is not in the range of arctangent. Arctangent, there is nothing that you can take the arctangent of that's going to get you pi. Okay? So that's going to be the big subject of the next lecture, with a ton of examples where we really hammer down on this. Look at all those letters. Okay, we're going to be doing a ton of calculations. Your calculator will be able to help for a ton of this, but it's really important, again, to get that conceptual understanding for as we move into chapter 9. Okay, and we're going to cut it here for now. Mostly theory. We did a nice intro to the section. Hope you enjoyed some mathematical fun, and thanks for watching.